Okay, let's quick review of section 2.2, rates of change. So we're going to look at a variety of problems here. We'll start off with a particle motion problem, and then we'll talk about people entering and leaving a museum. So we'll try and give you a couple different looks on the same idea. And generally speaking, when we're talking about rates of change, we're talking about the derivative. We're talking about how fast or how slow a function is changing. So in this first example, we have a ball or an object dropped from the roof of a building, and its position at any time during that flight is modeled by this equation. T is in seconds and S is in feet. So the first question is asking us to find the average velocity on the interval 1 to 3. And so when we do that, the first thing we have to understand is that we're not actually finding the velocity. I know it says velocity, but average velocity is talking about the change in your position over time. So what we would have to know then is where was the object at t equals 1 and where was the object at t equals 3. So in other words, we're going to basically do the average rate of change. So we would plug in 3 first, or we could plug in 1 first as long as you stay consistent with the bottom. And if we plug in 3 first, we get 366. And we plug in 1 next, and we get a position of 554. And then we're going to divide that by 2. And so when all is said and done, we get a value of negative 94 feet per second. That's my average velocity throughout the trip on that time interval 1 to 3. Now, finally, we're going to try and find the instantaneous velocity at t equals 1. Well, now we're talking about finding the actual velocity. So before we do that, we're going to need to find a velocity function. So we're going to have to say v of t, and we're going to have to find the derivative. So the velocity is the derivative of position, so negative 32t minus 30. And since they're asking us right now to find that velocity at a specific point in time, all we have to do is plug in 1. So we plug in 1 here, and that would give me negative 32 minus 30, and that would be negative 62 feet per second. So again, what that means is that is the actual velocity of the object at that one moment in time at t equals 1. Now obviously if it moved to like 1.2 or 1.3, the velocity would be slightly different. Let's stay with this problem. Let's look at a couple other things. Let's look at acceleration. So if we're going to find acceleration, we have to remember that the hierarchy is we start with position, we move to velocity. Velocity is the first derivative of position, and then acceleration would be the second derivative of position or the first derivative of velocity. So we're going to have to divide this twice, and we've already done half of that. V of t, remember, was negative 32t minus 30. So then acceleration would be negative 32, which means even if we were to try and plug in 3, the answer would still have to be negative 32. But now what are the units? Feet per second per second. So feet per second squared. And you'll notice that that's actually the acceleration due to gravity. So since we were dropping a ball or an object, that kind of makes a little bit of sense there. And then lastly, this question asks, when is the object at rest? So when we're trying to find whether the object's at rest or not, that would have to mean one thing. If it's resting, it's not speeding up or slowing down. Its velocity would have to be 0. So we can actually go back to the velocity equation and set that equal to 0. And when we solve that, right, as of right now, we get t equals 30 over negative 32. That doesn't make sense. Can't have negative time. Well, think about that. That must mean then that the only time the object was at rest was later on down the road in its flight. And so at this point, we have to conclude that it was at rest when we dropped it at time 0, and then when it finally landed all the way down at the end of its trip. That also means then that there was no change. Like for some objects, you would throw them up and then they would go back down. That would mean that at some point in that time interval, the velocity would have to be 0. But we're not seeing that here. If we really wanted to find a value in terms of like where it ended its journey, we can actually set the position equal to 0, and that would tell us when the object finally reached position 0 on the ground. Okay, let's change gears a little bit, because position and velocity and acceleration are good, but there are other kinds of changes we want to be aware of. There's all kinds of situations. So this function is modeling the amount of people in a museum at any given time. And we're going to actually try and figure out, well, what would be the difference in finding a prime of 8 versus a prime of 18? Well, here's the similarity. What they both indicate is we're supposed to find the derivative of this function and then plug in 8 and plug in 18. So let's do that, and let's actually find out what that gives me. So I need to start by finding a derivative. Now remember, this can be written, this part right here can be written as 6t to the 1/2. So when I apply my power rule here, I would get 3t to the negative 1/2, and then plus 5, and then the derivative of cosine is negative sine t. So we clean that up a little bit. That would be 3 over the square root of t minus 5 sine t. Now, in this case, what they're asking us to do is to plug in 8 to that derivative, or 18. And so when we do that, let's see what we get. So a prime of 8 will equal something, and a prime of 18, and I'm sure these are going to be decimal values, so let's take a look here. So for the first one, I got negative 3.886. Remember, we always want to go in at least 3 decimals. And then we'll get some units here in a minute. And then if we do the same thing with 18, let's see what we get here. And I see 4.462. Okay, let's talk a little bit about units. This would have to be people per whatever the unit of time is. So this would be people per, let's say, hour. Let's just assume t is in hours. People per hour. What does that then actually mean? Well, it means that the rate at which people are in the museum is changing at negative 3.886 people per hour. So that means at this point in time, at 8 hours, let's say, into the day, we're talking about the museum actually there being less people in there because we're losing about 3 to 4 people per hour. Whereas at the 18-hour mark, or like I said, if we were talking about minutes or whatever, days, whatever it might be, we're seeing an increase in the amount of people in the museum at about 4.5 people per hour. So good things to look at. Now you also want to be aware of how to do this kind of thing on your calculator because it simplifies things a little bit. So I have this function all set up in here. Okay, that's the original function. So what we want to do here is we want to actually ask it to do the derivative of this, and then after we ask it to do the derivative, plug in a certain value. So I'll show you what we would have to do here. We would say, go to math 8, and that would bring up the derivative feature. Say I want to derive the function y1. So if you notice what I did there, I went to vars, went to yvars, chose function and y1, comma, derive that with respect to x, and then when you're done doing that, plug in 8. And when we do that, we get exactly what we had before. So let's do it one more time so you can see what it's like for 18. Math 8, the derivative of function y1 with respect to x, and we're going to evaluate this at 18. And again, we get 4.462. So you're seeing all those values coincide with what we got by hand until we had the calculator at the very end there. But this is something you'd want to be able to do, especially when you get to the AP exam, because it'll be a little bit more efficient if it's allowed. Okay, so finally, let's look a little bit at the graphical analysis of this situation. Right here, I'm showing the graph of a position of a particle, and I'm asking, how do we sketch its velocity? Well, its velocity is simply how fast it's changing, right? So its position changed from 6 to 0 over 2 seconds, let's say, or 2 units of time. Then what we know is that this particular line segment had a slope of negative 3. So what we would want to do is indicate that during this entire time period, the velocity of the particle is negative 3, and that would be good here, or here, or here, or even here. The entire time it has a constant velocity of negative 3. And then that same dynamic is going on here. So here we have a slope of negative 3. Here it looks like we have a slope of, let's see, up 1, 2, 3, of positive 1/4. And then what's happening here? If its position is not changing at all, that means it can't be having any velocity. So its velocity must be 0. So all we're going to do to sketch the velocity is to sketch these values. These are the values of the derivative during these time periods. So let me actually move this graph out of the way. And let's see if it'll let me do that. Whoops. And we'll just clear out our values and bring this graph in. Okay, this is just a new graph where we would graph our velocity function. So from 0 to 2, the entire time, our velocity was -3. So we would say, okay, there we go. Then from 2 to 6, we had a velocity of +1/4. So we're going to guesstimate here, but let's say that would be like right around there. And then finally, from 6 to 8, the object wasn't moving at all. So we would just show a velocity value of 0. So hopefully this review of rates of change has been helpful.